So the partial is being done with this, partial is being done by this. So, okay, see if you remember like when we did, for example, the softmax, there were 10 outputs, right? As we work backwards, did we have to sum all the gradients due to the 10 outputs? Do you recall? Like if you go back, you'll see. So if there are multiple paths going forward, right? On the way back, we have to accumulate all of those. So that's the reason for the summation over there. Okay, but like I said, in the implementation, you'll see it's very easy for each one of those gradients that we compute. All we have to do is take the difference before we do the update. Okay, so this was for the dissimilar case, similar case. And here I tried to explain how if this was a neural network, then we have partial L over partial A over partial W. So we can relate this to our thing over here, meaning, okay, so in our case, this will be again sort of similar to like this part, and then partial dw over w. So this will be further partial dw over partial w, and the sigma a1 of I of w minus a2 of I of w really acts as equivalent of, just like the delta that we used to have previously, which was simply ai minus yi if this was a sigmoid function, okay? Which further, to compute the delta, remember we used to multiply it by the derivative of the sigmoid? Okay, so anyway. Okay, second part. Okay, so I gave you the algorithm, how it will work. Okay, now let's take a look at y equal to 1. Okay, so remember our first part of the loss function was half y minus 1 dw squared. So if y is 1, what happens to this part?
0.
It zeroes out. So only the second part is left. Okay, and let's pretend the case, so that you're not worried about maximum. And like I said, in implementation, maximum is very easy. If it's above a certain distance, we simply do not back propagate. Okay, so we can remove the maximum, so it simply becomes really half m minus dw squared. Okay, so if you did the derivative of half m minus dw squared with respect to, right? So this is what the loss reduces to. And then same thing, it will be partial L over partial dw, then partial dw over partial w. So partial L over w, this is really partial L over partial dw, right? So if you did with respect to dw, you can see 2 cancels, m minus dw. And if you further took the derivative of the inside with respect to dw, what will happen?
M would be 0 and the derivative of dw with the function of it.
No, if you took the derivative of the inside with respect to dw.
Minus 1.
Minus 1. So that's why you have the minus 1 over here. Meaning minus over here, m minus dw. Right? And does this part change from what we computed earlier? See previously? Okay. So does this part change? Partial dw, this part I meant. Okay, that was, there was a dw further, right? But this was, meaning partial L over partial dw before was 1 over dw and then this whole term over here. Okay, the 1 over dw got canceled because then we further multiplied it by partial dw over w. Okay. Sorry, this was dw before, and this was this one. Okay, so anyway, there is 1 over dw in this term over here, which previously, once we assembled it as partial L over W, disappeared. So let's go to that extra dW that we have in the denominator. Okay, so this is coming from where? Partial L over partial dW. Okay, sorry, not this one. This one is, okay. This part over here
Partial
is
dW by
partial L over partial dW, as we just did a minute ago, right? Then this part over here, all of this is partial dW over dW. Oh, sorry, over W. So this is the same as before. Okay, so as you can see, this is for the dissimilar case. Okay, pretend the dW came out to be slightly less than the margin. So pretend margin is 2. dW came out to be 1.2. So as you can see, this part did not change. This is the same as before, right? So essentially minus 0.2, so in this example, sorry, minus 0.8, right? If this is, pretend for 2 dissimilar cases, this came out to be 1.2, this was fixed to 2, so this will be 0.8 divided by dW, 1.2. So let me assume this came out to be close to 1. So my question is, how is this term different from the similar case, the rest of it? So how is this whole thing? So let me quickly show you the previous case. Okay, this was our partial L over partial W for the similar case. Everybody agreed? Okay. Now for the dissimilar case, compare this equation to what I just showed you. For the dissimilar case, what's the difference between this equation and the similar equation? Is this part the same? This way.
Yes.
So this is the only new part, right? So let's try to analyze this new part for the dissimilar case. If I pick M to be 2, let's pretend for a given set of dissimilar images, this came out to be 1.2. So what's the difference then? 0.8 divided by dW, 1.2. Okay, so whatever that number comes out to, 0.75 or whatever. Okay, or let me even make it, this was 0.9, and now this will produce, okay, let me just leave it the same way, it doesn't matter. Okay, so anyway, so won't this whole thing will be multiplied by negative 0.75 in this example?
Yeah.
So the what I'm trying to say is, when we do the weight update, there's a minus term coming over here, so that the direction is opposite. So in other words, what I'm trying to say is, as we back propagate, we do partial A1 over partial W minus partial A2 over partial W for the similar case. So this is what our gradient comes out to be with respect to W as an example. Okay, for the dissimilar case, what's the fundamentally, what's the difference?
Just a number is added, multiplied, sorry.
No, there's just a minus.
Minus.
So the update of the weights will be done in the opposite direction. Okay. So anyway, so I'll give you further hints as you try to build this. So your next assignment is going to be to implement the Siamese. The CNN, you will try to convert to your Python implementation, which hopefully you're already doing and halfway through, hopefully. Okay. And then, like I said, as you now incorporate this, this will make it crystal clear how it is maximizing the distance between dissimilar cases. So the loss function that we came up with in plain English, what is it accomplishing? Essentially maximize difference between dissimilar cases. And then what else? Minimize difference in similar cases. You guys agree? Like if two digits or two persons were supposed to be same, it will create a lower distance between them. Okay? So now let's go and try to intuitively understand the idea. Because like I said, as we go further, it's easy to get lost into the details of the math and details of the coding, but if you have a goal, then you can, even come up with your own way to improve it. So let me see if everybody understands, what is this Siamese doing? Okay, as I mentioned, if we do a CNN, as we flatten the output, then further we pass it through some kind of a reduction so that we can reduce the flattening output to 100 or 50 or whatever values. So let's pretend we came up with 100 values over here. So there's a couple of ways to think about it. One way to think about it is we essentially have reduced the dimensionality. Okay? Those of you who are in the computer vision, we just went through PCA and LDA algorithms, right? Which are dimensionality reduction algorithms. And there also we were feeding it an input and it was giving us the reduced dimensions. This is also doing it. Okay, so let's try to see what's the difference between the two. Which one might work better, right? Okay, so we gave it an input of 2. It gave us 100 values. Think of these 100 values as a single point in 100-dimensional space. Okay, so somewhere I can draw 100 dimensions, pretend this image is now being represented by a point. Okay, now I feed in, let's say, another 2, which is slightly different from this one. So this network will again, corresponding to this input, will produce 100 values. Everybody agrees? So my question to you is, if I now put that point in the 100-dimensional space, the second point over here, let me make it red, will it be closer in distance to this point or will it be farther in? Closer. So it will be closer, right? So as we keep training it for similar, dissimilar cases, what would you expect? So to make it easier, let's reduce it to just 2 dimensions. So so in 2 dimensions we can easily C, right, where each point is. So in 2 dimensions, okay, if this is x, y, okay, so we feed in the first number, maybe it came out to be here. We feed in the red, which is also 2, won't it come very close to it? Okay, and let's say in our data set we had 100 2's. So won't all the 2's will be clustered together? You guys agree? Okay, let's compare it to any other digit, 3 as an example. Would all the 3's be clustered together? Right, because distance between each 3 is small. What would be the distance between 2's and 3's? Relatively higher, right? Okay, let me ask you a question. If we take a look at each cluster, for the 2's, for the 3's, for the 4's, for the 5's, and so on, can you guess which 2 of them, if they are 2 different digits, will appear close, their clusters will appear closer?
3 and 8.
3 and 8 is a good one. So remember 3, somebody could write it like this. 8 could also be written, you know, somewhat, something like this. So yeah, 3 and 8 will come out to be closer. Anyone else?
1 and 9.
6 and 9. 6 and 9.
1, sometimes people write 1 as like this.
9.
1 and 7.
1 and 7 will come out, right? Okay, so anyway, now I have a question more for those of you who are in the computer vision class, where we discussed just now the LDA algorithm. What was the goal of LDA?
To combine the similarity for the each class.
No, what was the goal?
Did it classify?
Right, so if data belongs to dissimilar groups, what does it do?
Distinguish the similarity and combine the similarity.
Was to build classes further away from each other.
Further away from each other, right? So won't LDA also try to accomplish this?
Yeah.
Okay, so for those of you in computer vision, now your next assignment will be compare this with the 2-dimensional transformation of data and tell me how LDA and these are different. So anyway, so that's another interesting point. Once you guys get to that, then you'll be able to instantly tell me this is what's the difference between the two. So anyway, to summarize, what will happen is all this will produce clusters, as you guys have already seen, if we properly program it. And so let me see if I can quickly show you. Okay, so this is one of the famous papers where they talked about Siamese networks. 2006 is when they reported it. Okay, so LeCun and some of his students, right? So anyway, okay, if you take a look at the loss function over here. Okay, does it look similar to what we just did? So this loss function, does it look similar to what we just did? 1 minus y dw, there's a, but anyway, the only thing is they don't have a margin, which I think they described it later on. Oh yeah, here's where they further defined it. So this is what we just discussed, right? Okay, so now the only downside of the original research papers is they give you the loss function, then they don't tell you how to build a network, right? Same thing LeCun did when he presented, the CNN never gave us the detail where full convolutions are involved, partial convolutions or inner convolutions are involved. Those we discover only when we go and implement it ourselves. So same thing, when I looked at it first, I said, yeah, this is easy. But then I wanted to program it, and then it didn't work. So struggled for a while, but same thing, like I said, once we understand the distances and so on, then it's not too bad. So they don't give us any, derivatives and the deltas over here. But let me show you this picture over here to see if that makes sense. Okay, so do you see 9s and 4s are closer to each other? Right, so again, they did a two-dimensional. Oh, so they're only over here, they're doing 4s and 9s. Let me see if they did. And 9s only, 4s and 9s only. Okay, anyway, I'll pick another implementation next time and show you where, like I said, there will be clusters of 3s and 8s and 4s and 9s and 1s and 2s. There will be some overlap over here. So one of the interesting area of research is how do we further push it apart so that we can easily distinguish between 2 digits. Okay. So anyway, so let me go for 5 more minutes, then I'll give you a break. So now the next topic I'll describe is the variational autoencoders. So let me turn that down. Okay, so first let me briefly review autoencoders before we review variational autoencoders, and then I'll try to tie the two together so that you can see how they relate to each other. Anyway, so autoencoder is a very simple network. So this is unsupervised. And the idea is very simple. For example, let's say we have a digit 2. Okay, if it's a minced digit, remember this will be converted to 784 values, right? So we have 784 by 1. Okay, so then let's say we compress it, meaning in our hidden layer, let's say we use 100 neurons. Okay, so then after feeding into hidden layer of 100 neurons, then we further expand it further. So this is basically our encoder. This is our decoder. Okay, so this pretend has also 784 neurons in output layer. So once again, we feed in 784 values. So this is like a regular dense network, nothing special. Okay, we take it to 100 inputs, 100 neurons in the hidden layer, then 784 neurons in the output layer. Okay, so question is, what are we trying to do over here? Okay, and the answer is what we wanted to do is we want to make it learn how to recover. So first how to compress it, then how to decompress this data. So think of this autoencoder like a compression, decompression type of network. Okay, so we'll feed in a 2. Let's say the first, once we normalize it by 255, the value is 0.2, next one is 0.15, next one is 0.31, right? Okay, so the expected output of all the neurons over here will be exactly the same as the input. So 0.2, 0.15, 0.3, and so on. Okay, So we're not telling it which digit is it. All we are saying is this is the input. Make it learn the compression decompression so that it can recover the same data as neatly as possible. Okay. Okay, so anyway, training, it will be 100% same as a regular neural network. Remember, in a regular neural network, we have a hidden layer, we have expected outputs, so we have an output layer, right? And we feed in an input, and then we backpropagate from the expected minus the actual. So this is 100% regular neural network with the difference, we're not doing classification, we are trying to reconstruct the input data. So expected output is same as the input data, right? So here's the beauty of it. After we have trained it, okay, let's say we trained it for all the, how many training digits did we have? 1,000 in our small data set, but 60,000 in the full data set. So we trained it. Then essentially what we have taught it is how do we compress any digit. So if I feed in an 8 after it's trained, it will tell me what are the 100 numbers that best represent the compressed information for that input, right? Such that this decoder can recover the 8. So after you build it, if you plot, this will be a sharp looking 8. If you take a look, it will still be like an 8, but a little bit blurry, which is expected, some loss going on in compression, decompression. Okay. Later on, if we replace it by a very deep CNN, then you will see the reconstruction will be really neat. Okay. So anyway, what's the benefit of this? Okay, so let's say we trained it. After we train it, then we remove the output layer. Okay, so then we feed it to these 100 inputs to a regular classifier. So if we are doing digit classification, what will this be? For example, this could be a regular neural network with 50 neurons and 10 neurons, 50 in the hidden layer, 10 in the output layer, right? And how many outputs then? 10, right? So once again, we'll build this architecture in 2 steps. First, we will train the autoencoder, then remove the decoder part once we only have the compressed representation. So think of this compressed representation as the important features that we are making it learn. So because those are the 100 things that clarify what that digit is or distinguish one digit from another. Okay, then the rest of it tells us whether it's digit 0 or digit 1 or digit 2. So now there's no Siamese, it's just a regular. Okay, so pretend we build it. My question to you is, how will this compare to if I did not build an autoencoder? I basically go put 100 neurons in the hidden layer. I feed in 784. I put 10 neurons in the output layer. And using softmax in the output layer, I try to do the classification. You guys were already doing that, right? In one of the assignments, what accuracy did you get on 1,000 MNIST digits? 90 or something, or 91 or 89, right? So let's pretend it was around 90. Can you tell me, will this approach behave same as this approach, or this might be a little bit better? Okay, the answer is here, see, as we discussed, what does a neural network do with one hidden layer?
Classify.
It's a classifier, right? So if I have one class of data which looks like this as an example, another class of data which looks like this. So neural network essentially, if we pick enough neurons in the hidden layer, is going to create a decision boundary. If we pick enough neurons, then it can, come up with a very proper decision boundary that distinguishes the data as much as possible, right? So over here, when it's trying to create a decision boundary, that decision boundary is being created in which space? How big of a dimensional space? What was the input over here?
780.
So doesn't that mean every digit is a single point in 784 dimensions? So the neural network is essentially trying to separate the digits in the 784 dimensional space. Okay? So that's what was being done in a regular neural network. Over here, take a look at this neural network. What is it trying to do?
Trying to classify in 100 space.
Trying to create a decision boundary in 100 dimensional space. But that 100 dimensions were obtained how?
By compressing.
By making it learn what is the best way, compressed way that represents the data, right? Whereas here in these 784 dimensions, is every pixel equally important? Majority of the pixels don't even have to do anything with the digit, okay? So theoretically, you can convince yourself that this will be a better approach, right? Okay, now let's compare it to Siamese network. So my question to you is, okay, so this is the autoencoder approach. Now let's go to the Siamese approach. We have a CNN, we have some flattening layer over here. Then what do we do? Let's pass it through 100 neurons. Okay, as I mentioned, we don't actually put two networks side by side because the weights are the same. We basically feed one image twice in a Siamese network, okay? So if I feed in an image 2, how many outputs will it produce?
What do you mean by 100?
Okay, let's say the flattening was 256, then I put 100 neurons. So what is the size of the output for any given image? 100, okay? What was autoencoder doing?
Same thing, 100.
100, right? But will these 100 be same?
No. I mean, in the dimensionality of space, it's the same.
It's the same, but what is this 100 trying to do over here?
So it's trying to relate all the, learned.
Trying to find a linear combination for the image using 100 input.
Yeah, so basically, what is the best way to compress this data?
Taking a meaningful.
So that we can decompress it, right? So here the emphasis is on compression. Is it on recognition?